Have you ever just looked at a simple pill and really thought about the incredible journey it took to get to you? I mean, it's so much more than just mixing a few chemicals together. It is a super high-stakes, incredibly precise scientific process. And today, we're going to pull back the curtain and unpack exactly how modern science makes sure that every single pill is safe, effective, and works exactly the same.
Right? That's the million-dollar question. How do you get that perfect precision, but on a massive, massive scale? For a long time, the approach was, well, a lot of trial and error, but that's not how it's done anymore. Today, manufacturers use this really smart, proactive method called quality by design to get it right from the very beginning. You see, the modern journey of a pill doesn't actually start in a chemistry lab. It starts on paper, or more likely on a computer screen, with a crystal clear idea of what the final product has to be. That's the core concept here. You design the quality in from the get-go, instead of just trying to inspect for it at the end.
Think of it like a detailed architectural blueprint for the pill. Before anyone even touches a single ingredient, scientists create what's called a Quality Target Product Profile, or QTPP. It's basically a master document that lays out everything the final pill must do: its dosage, its size, how it breaks down in your body, all to perfectly match the original brand name drug.
Okay, so you've got this huge blueprint, but let's be real, not every single detail is equally life or death important. So the next step is to boil that big document down to the absolute, non-negotiable must-haves. These are called critical quality attributes, or CQAs. We're talking about the features that, if they're even a tiny bit off, could directly mess with the medicine's safety or how well it works. And these aren't just vague ideas, they're super specific things you can measure. Like assay. Is the exact right amount of the active drug in this pill? Content uniformity. Is that dose exactly the same in every single pill that comes off the line? And dissolution. Does it dissolve and release the medicine at precisely the right speed? You get any of these wrong, and the whole batch is a bust. It's that serious.
All right, so once you know what you have to get right, what's the next logical step? Well, you start imagining everything that could possibly go wrong. And this isn't about being a pessimist, it's about being incredibly prepared. It's like a proactive hunt for problems before they even have a chance to happen. This whole process is called an initial risk assessment. Scientists use all their knowledge and past experience to basically create a risk map. On one side of the map, you've got all your process variables. Things like ingredients, machine settings, even the room temperature. On the other side, you have those critical quality attributes we just talked about. The goal is to draw a line connecting any variable that could possibly cause one of those critical attributes to fail. Now, not all risks are created equal. They get ranked. A low-risk variable is something they understand really well and don't expect any trouble from. But a high-risk one, whoa, that's a huge red flag. It means there's some uncertainty there, and it absolutely has to be investigated with experiments to bring that risk down. And here's a perfect real-world example. Look at this. Something as seemingly simple as the particle size of the main drug ingredient gets flagged as a high risk for two different critical attributes. Why? Well, because if the particles are too big or too small, it could totally throw off both the dose consistency and how fast the pill dissolves. This tells the scientists exactly where they need to point their microscopes and run their experiments. So we've identified the big, scary, high-risk problems. Now what? Well, this is where the team moves from planning on paper to actually getting their hands dirty with experiments. But they do it in a really smart, super efficient way. Instead of that old, slow method of changing just one thing at a time, scientists use this powerful statistical approach called design of experiments, or DOE. Think about it like you're trying to bake the perfect cake. Instead of just tweaking the sugar, then baking a cake, then tweaking the flour and baking another. DOE lets you test different combinations of everything all at once to find the perfect recipe way, way faster. And the magic word here is interact. A DOE doesn't just show you that, say, pressure matters. It can reveal that pressure only really matters when the temperature is also high, or that one ingredient completely changes how another one behaves. It uncovers all these complex hidden relationships that are the real secret to making a bulletproof process. So the result of all these experiments often gets visualized in something called an overlay plot. The easiest way to think about it is like laying several transparent maps on top of each other. Each map shows the good settings for one critical attribute. The spot where all those good areas overlap, that's your target. That's the sweet spot. And here's what that looks like in the real world. For a manufacturing step called roller compaction, all those experiments revealed this incredibly precise green zone. It tells you that as long as the machine's roller pressure stays between 20 and 77 bar, and the gap is between 1.2 and 2.4 millimeters, the stuff that comes out will be absolutely perfect for making a great tablet. It completely replaces guesswork with a mathematical guarantee. Okay, so you have a perfect recipe that works like a charm on a small lab bench. That's fantastic. But now you're facing the next enormous challenge. How do you make that exact same perfect product, but on an industrial scale, turning out millions or even billions of tablets? And the jump in scale we're talking about is just massive. You might start with a tiny lab batch, maybe 5 kilograms. Then you move up to a 50-kilogram pilot batch to prove everything works. And finally, you scale up to the full commercial batch size, which could be 150 kilograms or honestly way, way more. And you can't just, use a bigger mixing bowl and hope for the best. Scaling up is a science all its own. Engineers use these principles of similarity to make sure the actual physics of the process, like how the powders flow and mix, stays exactly the same, even when the equipment is 10 times bigger. So let's recap. We've designed the product, we've identified the risks, we found that green zone, and we figured out how to scale it all up. The very last piece of this giant puzzle is creating a system that guarantees the process stays inside that green zone every single day for every single batch forever.
This whole thing gets wrapped up in what's called the control strategy. You can just think of it as the ultimate rulebook for manufacturing this drug. It's built from every single piece of knowledge we've gained so far. It specifies the checks for raw materials, what to monitor during the process, and what tests to run on the final pills.
And here it is. This is the big payoff. Remember that initial risk assessment way back at the beginning? A key risk was flagged as high, that the roller compaction step could totally mess up how the pill dissolves. But now, after all that development work and all those experiments, look at that. The exact same risk is now considered low. So why is the risk low now? It's not magic. It's because it's not a mystery anymore. It's now being actively controlled. All that development work proved that if operators on the factory floor see a change in a measurement called ribbon density, they know exactly what to do. They just adjust the compression force to keep the tablet hardness right inside that proven green zone. Knowledge turned a high risk into just a routine, everyday adjustment.
And this fundamentally changes the entire manufacturing game. You see, instead of making a gigantic batch of pills and just kind of crossing your fingers, hoping it passes a test at the very end, this new way creates a living, breathing process. Quality is built in and verified at every single critical step, making sure the whole system stays perfectly in control from start to finish.
So this whole meticulous journey, from a blueprint on a screen to a rigorously controlled industrial process, is what ensures the medicine you rely on is safe and effective every time. And it kind of makes you wonder, right? If we applied this same philosophy, this idea of designing for quality right from the very start, what other complex systems in our world, from software to building cities, could we completely revolutionize?